In this video, we're going to check out rational functions and see if we can identify some characteristics um, with these rational functions. And so what we really call this is interpreting rational functions. And when we say interpret, we just mean relevant characteristics. We want to make sure that we can look at a function and have an idea of what's going on with that function graphically. And I think anytime we can get a mental picture of math, of functions, of whatever, anytime we can get a mental picture, a lot of us are more inclined to understand what's going on with it. So these characteristics are the ones that we're going to identify. So these are the things that we have to know how to find. And if you look at these are really just review of a lot of the topics that you do either in Algebra 1 or Algebra 2. And so if you look at roots, we know how to find roots of functions. Asymptotes is an Algebra 2 topic. Holes, intercepts, all of those things are really Algebra 2 topics. This one you might be a little bit unfamiliar with, but we'll talk about in this video. And then domain, we just want to make sure that we understand what kind of values can we plug into this function and get real number answers or real number outputs out of the function. So these 5 things, these are the 5 we're going to concentrate on when we say interpret, and those should give us a really good idea of what's going on graphically. So this is really a graphical representation that we're trying to figure out here. All right, so let's get to it. So I've got a couple examples, and what I have up here for you is I've got the graphical representation up here. Okay, so we want to check this thing out, this function, and we've got the graphical representation over here. And so I kind of already have, based on seeing that graph, I've got an idea of what's going on with this thing already. Or at least I should. So number 1, I've got this asymptote right here, and this is a vertical asymptote right here. It looks like maybe it's at x equals negative, or yeah, x equals -1. Right about here. I've also got a horizontal asymptote where this function is going to approach it, a particular value, but never hit that value, never exactly be on that value or return that value. So I've got a horizontal asymptote and a vertical asymptote. So let's see if we can just take a look at this function and algebraically figure those things out. Okay, so the first thing that we're going to do is we're going to look at this original function. And we're going to look for domain restrictions on that original function, okay? So I'm looking at this thing and I'm saying, hey, there's a variable in the denominator. Let's make sure that we identify when we have a domain restriction, okay? So I need to take this denominator and I want to know when is this thing equal to 0, because I know that those are domain restrictions. I know the denominator can't be 0 because that gives me an undefined value. So I take the original, set that equal to 0. I know that when I'm going to solve this thing, I get x squared equals 1, and you take the square root of both sides, and you get x cannot be plus or minus 1. So if I plug in a plus or minus 1 there, I'm going to get an undefined value. So that's the first thing I'm going to do. The second thing I'm going to do is I'm going to simplify. And what I mean by simplify is I'm going to take this thing and see if I can factor the numerator and the denominator. So we look at the numerator and we say, well, that's kind of easy. I know that that I can factor that numerator into x minus 1, x minus 1. So there's our factor form for the numerator. Now we're going to look at the denominator and we're going to factor that thing. And we know that's a difference of squares, so that's x minus 1, x plus 1. So now I take a step back and I see, hey, I've got 2 things that can cancel here. I can cancel an x minus 1, I can cancel an x minus 1. And so this is a really important, this is kind of the first point in interpreting functions. I just canceled 2 terms or 2 expressions or 1 expression out of the numerator and the denominator. And that is one of my domain restrictions that I identified. So anytime something cancels, so if an expression cancels, that tells us that there's a hole in the graph. Okay, so we just got an x minus 1 to cancel. So we're going to identify that by saying, hey, x minus 1 can't be 0. We already knew that from above, but the hole in the graph is when x equals 1. So we go back up here, and I go to my graph, and this is one of the drawbacks of technology sometimes, is technology sometimes does not identify properly some of the characteristics, and so in this particular case, it's not identifying where a hole is. So I'm looking at this graph, and I know I'm going to go to x equals 1. There's actually a hole right here. We know there's a domain restriction, but there's a hole right there. We can't plug in that value into this function. Okay, so when I'm identifying domain, and I've now done all the work to identify the domain, I need all holes and vertical asymptotes. So vertical asymptotes and holes in the graph. All right, so what we're going to do when we interpret, we're going to state what the domain is. So I know that my domain is all real numbers such that x cannot be plus or minus 1. But I also want to state what be more specific about what these particular domain restrictions are. So I know there's a vertical asymptote at x equals negative 1. And a hole at x equals positive 1. So I've now taken my function, I've analyzed the domain, I've identified domain restrictions, and I've also specified specifically what are those domain restrictions from this particular function. So the next thing that we want to do, we've identified vertical asymptotes. We want to next look at horizontal asymptotes. So horizontal asymptotes, there are a couple different scenarios. Number one, what we're looking at is the degree of the numerator versus the degree of the denominator. Spelled that wrong. There we go. So degree of the numerator versus the degree of the denominator. So let me give you a couple quick examples here. Let's get this guy in here. A couple quick examples. If I have a function that looks like this, y equals x. Well, technically we know that's y equals x over 1. So what we're looking at is the exponent on the variable, the highest exponent on the variable in the numerator, and the highest exponent on the variable in the denominator. So the degree of the numerator equals 1 in this particular case, because this is x to the first. We also have the degree of the denominator denominator, that's equal to 0 because we have no variables. So technically this is x to the 0, 1 to the first. So when we compare these two, if the degree of the numerator is greater than the degree of the denominator, what we have is a case where there are no horizontal asymptotes. Okay, in this case right here, this is the simplest case of that. If you forget this rule, write this case, y equals x. We know that's a line. We know there are no horizontal asymptotes when you have a line. So that's the first case. The second case is if the degree of the numerator is equal to the degree of the denominator. So in this particular case, let's look at something where it's maybe 2x plus 1 over x. Now we know we can't simplify this anymore, so we're going to look at the degree of the numerator and the degree of the denominator. The degree of the numerator in this particular case, we're looking at this exponent right here. That's technically x to the first, so that's equal to 1. The degree of the denominator is also equal to 1 because we have x to the first. So in this case, the degree of the numerator is equal to the degree of the denominator. So when this happens, you get a scenario where you have to look at the coefficients. So there is a horizontal asymptote at And you're looking at the coefficients of each one of these numbers. So the coefficients of each one of the highest degree. So the term with the highest degree here is 2x. So I've got 2, and this is a y equals, and that's 2 over, and technically this is a 1 for this particular function. So just to generalize that, this is, you have a horizontal asymptote at y equals a over b, where a is the coefficient of the term of highest degree in the numerator, and b is coefficient of term, so I'm just going to put quotes here, coefficient of the term of the highest degree in the denominator. Okay, so that's your second case. If the degree of the numerator is equal to the degree of the denominator, you're going to look at the coefficients of the term of highest degree, and that's where you're going to find your asymptote, your horizontal asymptote. The third case here then is when you have something where the degree of the denominator is greater than the degree of the numerator. Let's move this down a little bit here. And when this happens, what you've got, and this is the simplest case of this, so this is the degree of the numerator is less than the degree of the denominator. And when this happens, we've got a case where there's a horizontal asymptote at y equals 0. Always y equals 0. We don't look at the coefficients in this case. Again, the degree of the numerator is 0 here. The degree of the denominator is 1. So this case holds. We've got a horizontal asymptote at y equals 0. All right, so what I did was just kind of take that stuff we just wrote about how to identify horizontal asymptotes. I put it on a separate slide for you guys so you can kind of see that. I'll post it in the notes. But let's go back to our example here. So in our example, we've gone through, we've identified vertical asymptotes, holes, and domain. And so now we want to identify horizontal asymptotes. Well, if you recall those rules, what we have here is a situation where the degree of the numerator is the same as the degree of the denominator. And so what does our rule say? Well, it says to compare the coefficients. And I'm looking here, I've got coefficients on terms of highest degree of 1. So I know I've got a horizontal asymptote at y equals 1. And the reasoning is, again, since the degree of the numerator is equal to the degree of the denominator. Okay, so we've got all these things. We've got vertical asymptotes, horizontal asymptotes. There was a hole in this particular one. So now we need to go find intercepts. And to find intercepts, basically what I'm going to do is just go through, and I'm going to rewrite my function here. F of x equals x squared minus 2x minus 1. This is where I'm going to take my function and actually use the simplified version of it. So we already simplified this thing, and we simplified it right here. So I now know that f of x is equal to x minus 1 over x plus 1. And so if I want to find my intercepts, and hopefully we're all pretty adept at this by now, to find the x-intercepts, plug in y, or plug in 0 for y. And when I do that, it gives me something that looks like this. 0 equals x minus 1 over x plus 1. So how do I solve this? Well, I can multiply both sides by x plus 1. And in fact, this is what we're going to do every single time. And what that leaves you with is just the numerator. the numerator x minus 1 is equal to 0. And this is what we can do every time. So we actually just have to set the numerator equal to 0 in order to find the intercepts, or in other words, the roots. So I've got a root here at x equals 1. Let's go double check. Up at the graph, there's my root, x equals 1. And we're done with the x-intercept. The y-intercept, plug in 0 for x. And so when I do that, I get a 0, I get y equals 0 minus 1 over 0 plus 1, which is equal to negative 1. Remember, we always list intercepts as coordinates. So my x-intercept is actually, this is 1, 0, and this is 0, 1. So there are my intercepts. There's an intercept. And we're done with this one. So long explanation as we go through, but they're a little bit quicker if you can kind of go through individually and figure out all of these different characteristics of the functions. The last thing that we want to do is condense all this information. And so the first thing that we start with is the domain. And we said that the domain was all real numbers such that x can't be positive or negative 1 in this particular case. We want to specify the characteristics about the domain, so we want to be a little bit more specific. So we know we have a vertical asymptote at x equals, I believe it was negative 1, and a hole at x equals, when x equals 1. Technically this is a coordinate, but we can list it like this, that's okay. The next thing is horizontal asymptotes. We know we had a horizontal asymptote at y equals 1. X-intercepts. Yeah, my x-intercept was 1, 0. And my y-intercept was 0, 1. And we're done. So this is all the information condensed. Make sure that you condense it and keep it organized. All right, guys, I'm going to do one more quick example just to give you another thing to look at here. But so again, the process is exactly the same. If you think back to the process that we took, we're going to look at this thing. We're going to identify, we're going to look at the original, identify any domain restrictions. So from here, I know that x cannot be 1. Okay. The next thing I'm going to try to do is simplify this thing. And when I simplify, I'm looking to factor essentially and see if any particular factors or expressions will drop off. Well, I know I can't factor the numerator or the denominator, so I can list there aren't going to be any holes, so I can list my domain. So my domain for this particular one, for this particular function, is all the real numbers such that x is not equal to 1. And in this particular case, what is x equal 1? That's a vertical asymptote. So specify, again, those domain restrictions, make sure that you specify. Okay. Next thing we want to do is identify any horizontal asymptotes. I know that the degree of the numerator is greater than the degree of the denominator. So what does that tell me? This tells me no vertical asymptotes in this particular problem. All right. Next thing we want to do is identify intercepts. So I'm going to go through identify intercepts. The first one, I'm going to look at x-intercept, plug in 0 for y, and again, all we have to do is take the numerator and set it equal to 0. So when I go through and solve this thing, I've got 2x squared equals 5. Divide by 2, I've got x squared equals 5 halves. Take the square root of both sides. Remember, when you take the square root, it is positive and negative of whatever you're taking the square root of. And our graph confirms that. Here's the positive version, here's the negative version. You need both of those. So there are my x-intercepts, my y-intercepts. My y-intercepts we're going to plug in 0 for x. So if you notice, it just kind of drops these x terms off. My y-intercept can be found by just looking at the constants. So the constants tell me I've got a y-intercept at 5, and the graph again confirms that. So the y-intercept is at 0, 5, and again, almost forgot to write this as a coordinate. And this is fine to write this as plus or minus 5 over 2, 0 for your x-intercept. So again, condense the information. My domain, x is in the reals, and I don't care if you guys initially just write this off to the side so you don't have to write it again. X can't be, what was it? X can't be 1 in this particular case. I've got a vertical asymptote at x equals 1. I've got a horizontal asymptote. It should be horizontal. No horizontal asymptotes. And I've got x-intercept, 2 of them, at plus or minus root 5 over 2, 0. Notice again it's written in coordinates. I've got a y-intercept at 0, 5, and you're done.